adders and says adder subtractor. See, we have binary digits, bits. So numbers can only be 0 or 1. It's very simple to add 0 and 0, 0 to 1 or 1 to 0, 1 to 1. So if you have two inputs, A and B, you want to add this. We have a sum. So we have AB sum. Well, yes. When both are 0, sum is 0. This is 0 and 1, the sum is 1. When both are 1, we are adding 1 to 1, it becomes 2. 2 is 1, 0 in binary. So I can only put a 0 here and this 1 has to be accommodated. So I have one more output called carry that we do in a paper and pencil addition also we do that. You are adding 23 to 84 decimal, 3 plus 4 7, 2 plus 10, but I can only put a 0 here, the 1 gets carried. The same concept here. Now, this is a simple circuit. You have a truth table. As you can see, sum is exclusive OR of A and B. And carry is A and B. This is my adder. Very simple circuit. One XOR, one AND. The problem is I am never going to add 2 bits. I am never going to add a 1 to 0 or 0 to 1. I can do it in my head. I don't need a computer, I don't need a hardware. I don't need a pencil and paper. So I need to add usually several bits. If you are an 8-bit representation, sign magnitude or 2's complement will have plus 120, minus 128 to plus 127, 2 such numbers to add. So we need a multiple bit adder. So when you have a multi-bit adder, this carry has to be fed into the next bit position. So these two inputs A and B alone are not sufficient. We need an extra input called carry in. If I am adding bit after bit after bit after bit, the carry from one position has to be fed into the second position. That is what happens in our decimal system also. You have a carry from one position, goes to the next position. Carry from that goes to the next position. So carry has to be propagated. So I need another input called carry in. So this is my A, B and C in. I have outputs, sum, carry out. This adder which does not take into account input carry is called a half adder. This adder which takes into account the input carry is called a full adder. In full adder, I have 3 inputs and 2 outputs, so my truth table will have 8 rows. This is my truth table. Sum is 0, carry is 0, sum is 1, carry is 0, sum is 1, carry is 0, sum is 0, carry is 1. First 4. Now it's sum is 1, carry is 0, sum is 0, carry is 1, sum is 0, carry is 1, sum is 1, carry is 1. This is the truth table of a full adder. I can draw the corner map for this, simplify it, get the logic. All this is not necessary. Now you have become experts in corner maps, how to draw a corner map from a truth table and how to get a terms from the truth table, corner map, and then how to draw it using gates. Since we know all of that, I will not go through this exercise. I will simply give you the circuit. This circuit will have one exclusive OR whose inputs are A and B, and another exclusive OR whose input is sum of this half adder sum. This is a half adder sum. A and B only gives you a half adder sum. But the carry has to be taken into account, so I need one more exclusive OR whose input is carry in. So the output is sum. So sum of the A, B and C n of a full adder is A exclusive or B exclusive or C, or 2 exclusive OR gates. And carry out is very simple equation. This is I can draw the K map for the carry out. This is 0, 0, 0, 1, 0, 1, 1, 1. This is A, C n, this is A, B, A, B, A, C n, and B, C. So that means I have 2 AND gates, 3 AND gates, AB, AB, AC in, BC in. Feed all this into an OR gate. This is carry out. So full adder has 2 exclusive ORs for sum, 2 input AND gates, 3 2 input AND gates, 1 3 input OR gate for the carry.